In this module, our focus will be on multiple regression analysis. Compared to simple linear regression, multiple regression allows us to take into account numerous factors, thereby enabling us to achieve more precise and accurate estimates. The mathematical representation of multiple regression articulates how the mean value of y correlated with x1, x2 to xq. Similar to simple regression, beta 0 symbolizes the intercept. Each slope coefficient, denoted as beta z, signifies the shift in the average value of the dependent variables y in response to a 1 unit increment in the independent variable xj, while keeping the values of other independent variables unchanged. The predicted values of the dependent variables y are calculated by inserting the values of the independent variables x1, x2 to xq into the estimated multiple regression equation. In the context of simple regression, we can employ a two-dimensional graph to portray the linear line and its residuals. However, visualizing the estimate equation in multiple regression becomes more challenging, given that there can be an arbitrary number of independent variables. When dealing with two independent variables, we can utilize a three-dimensional graph to illustrate the residuals, which are the discrepancies between the actual y values and the fitted values on the regression plane. In the calculation of the coefficient values, as with simple regression, the least square method is used to form the estimated multiple regression equation. As a consequence, the coefficient of xi is determined by dividing the covariance of x and y by the variance of x. Due to the computational complexity involved, we generally depend on computer software packages to derive the estimated regression equation and establish the regression coefficients b0, b1, b2 to bq. As we will relying on computer software packages for these calculations, the emphasis in this module will be placed on interpreting the computer output rather than performing the multiple regression computations. In this heating cost case, our objective is to determine the expected cost of heating a home in the winter based on three independent variables: the mean daily outside temperature, the number of inches of insulation, and the ages of the furnace in years. Assuming all three independent variables are relevant and should be included in the model, we construct a multiple regression model as shown here. This implies that the heating cost is a function of the outside temperature, insulation thickness, and the age of the furnace in the home. In this case study, data from a random sample of 20 homes has been gathered and the variables has been defined. We are now ready to employ statistical software such as Excel's data analysis tool or SPSS to compute the necessary statistics for the analysis. After running the regression, we obtained the following coefficient table: the regression intercept, A is labeled intercept in the Excel output. The regression coefficient for mean outside temperature is -4.583. This means if we increase the temperature by 1 degree, while holding the other two independent variables constant, we can estimate a decrease of $4.58 in monthly heating costs. The -14.831 indicates that for every 1 inch increase in insulation, we can expect the cost to heat the home to decline by $14.83 per month. Furthermore, for each additional year the furnace ages, we expect the cost to increase by $6.1 per month.